So this lecture and really this module is all about debugging. So debugging is after you write your code and you try to run it and it doesn't work, trying to fix the code. And not just your code, really. I mean, in general, with these IoT devices, there's code, there's the software part, but there's also the hardware part. And you have to debug them both together, which adds complexity. We're just talking right now about the software part. We'll get to the hardware part later and how to debug that. But right now, given the code, how do you debug that code? And you can expect that a lot of your time will be spent debugging when you write real pieces of code. I mean, right now, we're working with the Blink example, little things like that, no big deal. But when you get to complicated pieces of code, probably you'll spend more time debugging than you spend writing the code in the first place. It's very common in complicated pieces of code. So we'll talk a little bit about how to do debugging and what's required. Debug and trace. So one thing about debugging and testing in general and debugging is that you require controllability and observability to locate the bug. So what do I mean by that? Controllability is the ability to control sources of data that are used by the system. Okay? This you need in order to apply tests, to test something to see if a feature works. So when I say source of data used by the system, what do I mean? So the main source of data used by the system is going to be the input pins, right? If you want to do a test case, you have to be able to apply some value to the input pins. Now, this might be done through your sensors, right? So for instance, say I've got a switch connected to the input pins. I can flick that switch off and on and control the input pins that way, which is the best, right? Or say I've got a light sensor or something like that, and and it's connected to some pins. I want to control that. I can change the lighting in the room, right, and control the pins in that way, indirectly. So the input pins are your main interface. And if you want to do a test, you say, well, I wonder how my system works if the switch is flicked on and it's very bright in the room. Then you can set that up and power it on and run it. And that's a test case. And then you can try other test cases, right, to detect the bugs. So that's what I mean by controlling the data sources that the code is using. Now, the input pins aren't the only thing that you would like to be able to control. In addition to that, you would optimally like to be able to control the internal data, meaning the storage elements, the registers, and the memory inside the chip. Now, we won't be doing that in this class. I'm just saying optimally, if you're doing this professionally, you don't just say, let me control the pins. You go straight into the device and say, OK, I'm going to set this register value equal to 10 and see what happens. Right? I'm going to write some data into this memory location and see what happens. You would like to be able to do that. It gives you much more precise control over the behavior of the system because doing it through the input pins can be indirect. But optimally, that's what you would like. So that's controllability. Controllability allows you to do testing, to test certain circumstances that you think might be causing a bug or triggering a bug at any rate. So in addition to controllability, you need observability. Now, observability is the ability to observe intermediate and final results. So what do you need to observe? First thing you need to observe are the output pins. The outputs of the whole system. You need to see what values are on those pins. Now, often you can observe these directly through the actuators. So say the output pin is connected to an LED. You look at the LED, you can tell if the pin is high or low, right? Something like that. You look at say it's wired to an LCD screen. You look at the LCD screen, and you can tell based on that, you can infer what type of data is on those pins. So you want to be able to observe the pins. You can also directly observe the pins if you take a multimeter and wire it straight to the pins. Multimeter, basically, you can read the voltage and the current and the resistance. So you can just read the voltage off of the pins and see what the voltages are. So that's a more direct way of reading it. Now, another way to do it, and we won't be doing this in the class, is using an oscilloscope. So if an output pin changes slowly over time, then a multimeter is fine, right? Multimeters are changed slowly too, so that works. But if the signal is changing fast, say every millisecond, let's say, you can't see that on a multimeter. You would need to use an oscilloscope. An oscilloscope basically shows me the voltage over time. So you'd wire it to an oscilloscope, and you can observe the data that way. So the outputs are something that you would want to observe, and we have ways of observing the outputs. At least if they're slow changing, we can observe them through whatever the devices are, maybe a multimeter, but also whatever the output devices are, whatever the actuators are. Now, again, you would also optimally like to be able to observe the register content. So you'd be able to like to be able to look at the register values at a certain point in time, see what they are. Like after a certain instruction, maybe say, oh, what's in this memory? right, to see what the intermediate results are. We won't be doing that in this class, but optimally you would like that. So you need controllability and observability somehow in order to do testing and to do debugging. And we're primarily going to do that through the input and output pins. So now, okay, so we're doing it through the input and output pins, and the next slide says I/O, input and output access, is insufficient. So that's maybe a strong term. Not insufficient. It is maybe more difficult to debug through only the inputs and outputs, but with the level of difficulty that we're dealing with in this class, input and output pins are generally sufficient for that. But if you're doing this professionally or making bigger pieces of code, just look at the input and outputs will probably not be sufficient to do debugging. It will make debugging much harder. So here's a little example. Say you've got some Arduino program running. And the Arduino, you're using pins 0 and 1 on the left side, pin 0 and 1 as the input pins, and pin 2 is the output pins, wired to some actuator, whatever it is. Now in between, inside the Arduino, you've got some code running, and those blocks are showing the code running. So you see 3 blocks, main and foo and bar. Those are 3 functions. There's a main function, which calls a foo function, which calls a bar function. 3 functions inside your code. Now, let's say you run your system, and the output is on pin 2. So you look at pin 2, you look at its value, say it's wired to an LED, and you see that it has the wrong value, right? So if it has the wrong value, how do you know where the bug is? Like the bug could be in the main function, it could be in the foo function, it could be in the bar function, or it could be in some nasty combination of the 3. So, but how do you zero in on where the bug is? Just knowing that the output is wrong, that pin 2 is wrong, doesn't give you much information as to exactly where in the chain the problem happened, what part of your code it happened. Now, if you have a small piece of code, like the Blink example, you're talking to 5 or 6 lines of code or something, so who cares? But if you have a real piece of code, then you need more direction than just the output is wrong, right? You need to know exactly where it went wrong, maybe which variable had the wrong value in the variable stored in memory somewhere, So I/O access for big systems is insufficient for doing debugging, but for what we're doing, it's what we have and it's efficient. Okay, so properties of debugging environment. So what would you like to have in terms of debugging environment? And what I'm talking about here is really optimal in terms of if you're building a bigger system or more complicated system, what you would like. We don't have this, okay, for the Arduino, but this is what you would like. This is what professionals have. So run control of the target. Run control of the target is very useful. And in fact, now we won't have it for the Arduino, but when you write code, you've got to have run control. If you just write C code on your desktop, laptop, you can get run control. So by run control, I mean you've got to be able to stop and start the program in the middle. Not just wait till the end, wait till it's done. You want to be able to stop the program dead in the middle, and at that point start looking at variables, let's say. Looking at register values, look at memory contents, that type of thing. So it allows you, having run control allows you to look at the intermediate values manually. So, so generally this is done using breakpoints. We won't be using breakpoints, but breakpoints are basically, you look at your code and you see something's gone wrong and you have a suspicion. Oh, I think the problem's somewhere around line 53. So you set a breakpoint at line 53 and you let the code run until line 53. Then it stops, and at line 53 you can then type in, or depending on your interface of your debugging environment, you can look at the values of the registers, the values of the memory, the values of the variables when you're at line 53. And then you can step through the code. You can say, okay, execute one more line. Let's look at the values now. And you can keep looking at the values until they go wrong. You can say, oh, now value X has a wrong value. I know it happened on line 54, something like that. So that's run control of the target. We don't have that for the Arduino Uno anyway, but that's a very useful thing to have. Real-time monitoring of the target. So what we mean by this is that say you use the run control on the target, it alters the timing execution of the target. So what that means is that, say you got a piece of code, and generally that code, say you got a loop, right, the loop function, and it takes 1 millisecond to execute the loop function, let's say. So if you do run control and you set a breakpoint in the middle of that, it runs for half a millisecond, you check things, and you run it for another half a millisecond, but the total execution time is now much longer because you stopped it and did some debugging and checking, right? So you have now completely altered the timing, the performance of the system. Now, in a system like in IoT devices, a lot of IoT devices, the timing is very important to the correct operation of the system. If you don't get the timing right, it doesn't work. So real-time monitoring is what you would like. Real-time is where you don't stop, you don't set a breakpoint and just stop the execution. You view data about the execution in real time, right? As it is executing, you are viewing the data. So for instance, say there's a value x, a variable x. You don't have to stop the program and then say print x. You can just see x coming out on some pins while it's executing. Without slowing down the processor, you can still see the value of x, let's say. That's runtime monitoring. Very useful. We don't have that, but very useful. Now, it's not intrusive in terms of performance, and that's very important for our timing-constrained systems. And there are many IoT devices where timing is important. And then related to that is timing and functional accuracy. So again, this is also related to the timing. What this is referring to is the fact that sometimes the way people debug is rather than running the code on a real system, they simulate the code. Now, if you simulate the code, the simulator usually doesn't run at the same speed as the actual system. So you're altering the timing performance just because you're doing simulation. So you want timing and functional accuracy. You want the simulated version to be exactly the same in terms of timing as the original. And you want functional accuracy. So another thing about simulators is that often simulators, they model most things, but there are certain things they can't accurately model. So they can't do certain behaviors. For instance, if you're doing a simulation, simulating an analog to digital converter is very hard. So sometimes simulators won't do that. So sometimes it'll be inaccurate in its results for the A to D conversion. And you might be doing an analog read, and then your analog read data will be incorrect because the simulator wasn't accurate enough. So you want accuracy in terms of timing and in terms of functionality, if you can get it. Thank you.